All right, this is Physics 1C for March 16th. Today we're going to be talking about capacitors. So I guess the first thing to talk about is just kind of what is a capacitor. Let me get my thing set up so I can see chat and everything. So capacitor is a type of device that's going to kind of store energy. And they tend to kind of act kind of similar to the way that a rubber band acts, where, you know, if you stretch a rubber band, there's energy stored inside of it. And if you let go, that energy can obviously be released. And, you know, you can use rubber bands to make different kinds of things, like little cars that move around. When you pull them back, they wind up and they gain some energy. Capacitors, they basically are just devices that can kind of store energy. I think I need to zoom out a little bit here. So let's go a little bit big. And these things are going to all be too close now. Okay, so we'll just say that it's a device that stores electrical energy in the form of basically electrical charges. This is still, I need to zoom out some more, I think. I'm just not going to worry about the stuff on the right side. Yeah, so capacitors are basically found in all kinds of electronic devices. If you were to open up any type of electronic device, you'd probably see some kind of capacitors inside of it. If you want to know kind of what they look like, this is kind of what they look like. If you ever opened up, a radio or an amplifier or your computer or anything like that, and you've seen little, they're really tiny. These look bigger than they would actually be, although stuff like this can be very large. They kind of look like batteries, right? Like this one especially kind of looks a little bit like a battery. And that's because capacitors can basically store energy just like a battery can, you know? Batteries have a positive and negative side. Capacitors have a positive and negative side. They don't have the same type of chemical drive that can cause charges to move through a circuit, but they can definitely be used to... see, this might be the more common type you might see right here that might be plugged into a circuit board or something like that. Have you guys seen... Has anyone seen these before? This is a really good example of one. You've never seen these before if you open up something? Okay. So we want to learn kind of what they do, why we use them, and all that kind of stuff today. But we'll just start off by saying that there's a lot of kind of applications of these things. They're found in all types of devices, right? So the places where you find capacitors, so capacitors can be used to deliver a large amount of energy in a very short burst. So one example is in pulsed lasers where you want to have a big burst of light energy coming out. You store up a bunch of energy in the capacitor and you can release it very quickly. They're found in like audio amplifiers. I kind of already mentioned that. Inside of your phone, capacitors are, and inside of your like laptops and stuff like this. If you're using a Wi-Fi radio right now to get access to the internet, then you have some type of a capacitor that's used for that. So I'll just say Wi-Fi and radios always have capacitors inside of them. It's one of the key components of how a radio works and how we transmit radio waves, transmit and receive radio waves for that matter. They're used because they can be used for gigantic bursts of energy. They're also used for flash photography inside of a camera. When the flash goes off, commonly there's a lot of energy that's been stored in a capacitor. If you ever used one of the old disposable cameras, or really any kind of old camera, you know they have that button on the front that has... I don't even know if any of you have ever used disposable cameras, so I guess I should ask that before I even... You all have used... Okay. Because because I'm sure they've been pretty much. Wait, there's like a little button on the front, and it's got a little lightning bolt next to it, right? And that's the flash button. You have to hold it down, right? Or you have to push it, and you'll hear this charging up sound that occurs, right? And it sounds like this kind of like loud whirring sound that grows higher and higher and higher in pitch. Is that something that you all can remember? If we were at the school, I would show this to you, because we have
I definitely remember that.
So we've got some old cameras at the school, and what we'll do is we'll basically show you how they charge up. Anyway, what happens is that through the use of some kind of crystal kind of resonance that occurs, they use a crystal to kind of like charge up these two plates. Just like if you were to open one of these things, they have really big versions of these type of capacitors that we saw right here, like kind of like well, like this size, but they're probably, I don't know, they look like the size of a small battery, like half the size of a AAA battery, maybe, or something like that, maybe bigger. Anyway, yeah, but that's something that that's the capacitor being charged, basically. And then when you push the flash, when you take the picture, and the flash of energy comes out, the capacitor gets discharged. So capacitors are all about being charged up, holding energy for a moment, and then being discharged when you want to use them. So hopefully you can see how that's similar to the way that maybe like a bow and arrow works, right? Where with a bow and arrow, you pull the bow back, you pull the arrow back in the bow, you hold it until you're ready to release it, and then you let go. That's basically what a capacitor does for us in electricity. It does other things too. It can also basically introduce timing elements. So in your car, if you have windshield wipers, there's different settings for windshield wipers, right? You have the really kind of very slow setting. You've got the intermittent setting where it washes the window, and some time passes, and then it washes the window again. Some time passes, washes the window again, right? In those type of circuits where you need, I'll say timing in, we'll say windshield wipers, for example. So something similar is going on there. There's a type of capacitor that's being used along with some other elements, such as a resistor, in order to control how quickly those wiper blades basically sweep across. And you can imagine that there's like some capacitor in the background that's charging up. It fills up, and then the wiper blade goes off. It's discharged now. The capacitor blade charges back up. It takes some time, and the wiper blade goes off. So it introduces a timing element, right? It introduces the ability to kind of count how much time before the next thing needs to happen. And it's a very controlled and precise amount of time that's going to occur. I'm sure when you use your windshield wipers, which you don't have to use very much, obviously, here in Los Angeles, but when you use them, the rate at which those things are sweeping back and forth is very consistent. And it's controlled by capacitors. And when you switch the knob, or whatever you're switching in order to change the rate at which the wipers are going back and forth, when you're rotating that knob, physically what's happening within your electrical system is it's changing this thing we call capacitance, which will then change the timing. And we'll learn all about how this works in this class. Okay, so what else is used in? They're used in computer memory. They're used in touchscreens, your touchscreens on your phones and stuff like that. When you touch the screen and it acknowledges where your finger is and stuff like that. It's also related to capacitance, which we're going to see here in a second. Turns out that when you touch something like that, it leads to a voltage change, which we learned about last week. That voltage change can be interpreted by a computer as there's a finger there, right? They're also used inside of keyboards. So like when you push down on a keyboard key, I don't know what you guys can see here. There's my keyboard. It's all black. You can't really see it. But when you push down on a keyboard, there's commonly, not all keyboards are made like this, but there's commonly some type of a capacitor that you're depressing. And we're going to learn that when you have a capacitor and you try to squeeze it a little bit, it's going to lead to a voltage change. That voltage change can be read out by a computer, and it can be interpreted as a keystroke, right? It can tell if you pushed a Q or a T or a 6 or an asterisk or whatever, right? So capacitors are used in all kinds of things. And this will be true for some other stuff that we're going to learn about over the next few weeks. So capacitors are what we call a passive circuit element, and there are going to be 3 or 4 that we talk about in this class. You can't see my camera today. Oh, am I sharing the wrong screen?
Yeah, we can't see your face cam.
I probably put the wrong thing on there, didn't I? I probably just sharing my OneNote or something. Were you able to see? You were able to see the Google Chrome and stuff like that, though, right? When I went to like show you.
Yeah. Capacitors, yeah.
So I'm just sharing screen. I got to share OBS. Where is it? There we go. Okay, there we go. All right. Thank you for letting me know. Sorry about that. Okay. So, you didn't miss anything. I was just waving my hands around and stuff like that. Okay, so these are how capacitors are used. This is why you should care about them. What I was trying to say is that a capacitor is one of several what we call passive circuit elements. It's a passive circuit element. There are going to be two more that we talk about. One of them I've mentioned quite a bit. It's called a resistor. It's the thing that is kind of what slows down the rate at which charges flow and kind of dissipates heat. Resistors are very commonly found in like toasters and electric stoves, stuff like this. And the last one will be an inductor, which is going to allow us to transfer energy between magnetic energy and electric energy. And so we're going to be talking about these throughout the class. It's called passive because it doesn't it doesn't actively do anything, but it responds to electrical signals and things like this. Okay, so capacitor. The symbol that you're going to see when you're doing your homework, and if you were to look online at like some kind of a diagram, is this right here. This is the symbol that we use for a capacitor. It's a type of representation of what we will often use in this class as the simplest version, which is known as the parallel plate capacitor. Okay, I've mentioned the word capacitor before because one of the simplest types of capacitors you can have is if you have two metal plates and you put a bunch of positive charges on one plate by connecting them to a battery, you put a bunch of negative charges on the other plate by connecting them to the battery, and this is basically what a capacitor is. It's like two pieces of metal that are separated by a type of insulator. So we can basically define that in a more specific way. So it's a device that stores energy, right? But a capacitor is basically just made from any two conductors that are separated by an insulator. Sorry, I need to move some things around here so I can actually see the chat. So that's what you need. You need two conductors. They need to be separated by an insulator so that the charges from one conductor cannot get to the other conductor. I've got a little picture from your textbook. I think it's from this textbook. It could be from a different one. I'm not sure. But here's kind of a picture. Zoom out a little bit more. Get these things off the screen. Okay. So here's a little picture. And here's the idea. So you start off with a wire. So here's a wire, this black line. Here's a switch. So we haven't talked about switches in this class, but a switch is basically just a device that can either open or close your circuit. So in this configuration right here, this little lever can be lifted up or down. And when it's switched down to this here, like here, then that allows the circuit to complete. So this would be a piece of metal, another piece of metal, separated by some kind of small gap in between them here. This is an oversized picture, by the way, that's designed for educational purposes. This is not in any way supposed to be representative of a real capacitor. Although we do have in the lab a capacitor that looks like this, which is basically just two circular discs that you can basically move in and out. Anyway, so here's a battery down here. The battery is going to have some voltage. You know, this voltage is represented in this picture by delta V, but if that's hard to think about, you just think about it as a number. Maybe this is like a 9-volt battery, for example. And if you connect the battery to each of these plates right here, what will happen is that's what's kind of shown in this picture right here. The positive side of the battery will basically positively charge one side of the capacitor. The negative side of the battery will negatively charge the other side of the capacitor. And it will set up an electric field between the plates. Because when you have a positively charged plate and a negatively charged plate, you get an electric field between those plates. Does anyone remember how big that electric field is?
Sigma, or its charge density divided by epsilon naught.
That's right. So the field inside of here is going to be completely dependent upon how densely packed these charges are, right? So if you pack on twice as many charges, you'll get twice as big of an electric field. Okay, so capacitance is all about how many charges can you actually pack onto here per unit voltage that you're given. Okay, so the bigger the voltage source that you have here, I think it's reasonable to assume that you would get more charges, right? So the capacitance is going to be related to how much charge you can store per unit voltage, and I'm going to define that here in a second. But let's look at why this happens. Whenever you connect up the battery, there's, as they say here, there's an electric field in the wire on this side that's going to tend to push positive charges this direction. Now, positive charges aren't really moving, but it's actually, negative charges are basically flowing back this way, but still, it doesn't really matter. This electric field is going to drive positive charges to here, but they can't go any farther, right? Here's what it says. Electrons from the plate to the wire, leaving the plate positively charged. Oh, sorry. Electrons move from the plate to the wire this way, back to here, leaving the plate positively charged. And then on the right side, electrons from the wire, electrons move from the wire onto the plate this way because there's an electric field that goes this way. As a result of this, the chemical energy of the battery gets reduced, and now you have a charged capacitor that we can do something with, okay? So we want to define what capacitance is. And what we can say is that we know that the potential difference between these plates is proportional to the electric field between the plates, and that the electric field is proportional to the charge on the plates, which means that the charge on the plates is directly connected to the voltage down here. And what we say then is basically that the amount of charge that we can store on these plates is going to depend on the size of this voltage source, as well as it's going to be a function of the plates themselves. For example, the larger the plates are, the more that you're going to be able to store, and it's going to turn out that the closer the plates are together, the more energy you're going to be able to store. So we define capacitance like this. We use the symbol capital C, and it is defined as the amount of charge Q that you can store on the plates. When you store charge on these plates, one side is always going to be positively charged, the other side is going to be negatively charged, and they're going to carry equal amounts of charge. There's going to be an equilibrium that's reached where the charge here and the charge here is going to be the same. When you have a positive and a negative charge on both sides, we say that the capacitor stores charge Q. So we don't care that in reality, if you were to look at the whole capacitor, the total charge would be 0, right? We still say it carries charge Q. All right. And based on that amount of charge, we can define the capacitance as being the charge that it stores divided by the potential difference across the plates. So it's effectively charge per unit voltage, right? And capacitance has a unit of 1 farad. So farad is named after Michael Faraday, who was a very, very famous British scientist that came from very normal means. His family was very, very poor, and he managed to kind of become a scientist through apprenticing with people, and he ended up having a massive impact on the field of electricity because he was responsible for discovering the connection between how electricity and magnetism affect each other that we now know as Faraday's law. He's also the person that invented the idea of electric field lines, which he called lines of force, which are incredibly useful to understand not only electricity, but Maxwell later used them to help to understand the way that electricity, magnetism, and light are all connected to each other. So Faraday is an absolute giant in the history of science. And one thing about Faraday that's really interesting, for those of you that are struggling with math in any way, Faraday was really, really bad at math. And he focused more on just using experimental setups to understand things. So he literally would just go into the lab and he would play with different arrangements of conductors and magnets and try to figure out what the best way to make them interact with each other. And so he was a pure experimental scientist who, in combination with Maxwell, they're both very responsible for our understanding of electromagnetism today. So 1 farad is the unit of capacitance, and it is defined as 1 coulomb per volt. So 1 farad, I'm still on the eraser tool, is equal to 1 coulomb per volt. And you could work this out in base SI units if you want to. You could replace the volt as being a joule per coulomb, and this would become something like coulombs squared per joule, and you could write the joule out. But it's probably going to be easier to think of it as a coulomb per volt. Okay, so that's our definition of capacitance. We say a capacitor has a capacitance C. We measure it in farads, and the farad is shortened by F. Normally what you're going to see is capacitors that are going to be much smaller than 1 farad. A 1 farad capacitor is gigantic. You're usually going to see stuff like this. You'll have capacitors that will be labeled as like 330 microfarads. I don't know if on this picture, if we can see on any, you can see it on this one here actually, right? You see how it says 2200 microfarads, and it looks like there's a temperature range from -40 to plus 85 degrees Celsius. And this is a polarized capacitor, which means that I believe this has to be the negative side. But yeah, they'll usually be labeled on the actual device what the value is. This one looks like 1,000 microfarads. So microfarad tends to be the much more normal. That's 4,200 microfarads. We have some in the lab that look like this, and they are like 6,000 microfarads. I think it's kind of the biggest ones we have in the lab. So a 1 farad capacitor would be gigantic. Kind of like how coulombs is a lot of charge. Okay, where's one node here? There we go. Okay. So that's the definition. And the larger the value of the capacitance, the more charge that you can store. Okay? So let's say, for example, I have a capacitor that has this value, 330 microfarads. And let's say that I connect it up to a battery that has a voltage of, say, 9 volts, for example. You could calculate the amount of charge that would be stored on such an object by just taking Q being equal to C times delta V. This usually is how I memorize this equation. Q equals V times C. So if you wanted to figure out how much charge was stored here, I should have picked a better number, but whatever. The capacitance, you just take 330 microfarads, and you multiply by 9 volts, you get some kind of a number here. $329.70. Thank you so much. Oh, and the unit will be microcoulombs. Okay. So what we're going to do is we're going to talk specifically about what we call a parallel plate capacitor. And then I'm going to show you some kind of animations of kind of what a capacitor can do. Okay, so let's talk about the parallel plate capacitor. Anyone have any questions so far? All right. So the parallel plate capacitor is something that we've actually been studying quite a bit, actually. The idea is you take, I don't want that one, I want like a line like this. So you take 2 plates, get this green. So I've got 1 plate there. We'll put another plate next to it that's separated by some distance, like that. I guess that's fine. We're going to say that we store it up with charge by connecting it to a battery. So we're going to say one of these plates is going to end up being positively charged. The other plate's going to be negatively charged. And in order to make that happen, we need to have some kind of a voltage source. So we'll connect each of these up with a wire over to a battery. So here's our battery. Let's say this is the positive side of the battery, this is the negative side of the battery, and let's say that is a 9-volt battery. Okay, but we're just going to call that delta V for the calculations that we're going to do so we can get a general result. So there we go. Put back on, yeah. So we connect this up, it charges up our capacitor like this, and it's going to have the capacitor be carrying on the left side some positive Q charge. On the right hand side, it's going to be carrying some negative Q charge. And in between the plates, there's going to be an electric field that's created, pointing from positive to negative. So let's draw electric field lines in here. The electric field lines will basically go from here to here, between these plates. And as Cam mentioned earlier, we know exactly how big these electric fields are going to be. So there's our electric field. We need to introduce some variables now here to represent our capacitors. So we're going to say that the area of this capacitor plate is A, as well as the other one. Okay, so this is going to represent the area of the plate. The plate could be a circle, or it could be a rectangle or a square. It doesn't really matter. We just need to know what the area is. And the other thing we need to know is we need to know the distance between the plates. So let's call the distance between the plates D. So we've got charge on the plates, the electric field, delta V, D. Oh, and the other thing we need is the capacitance. So we're going to say the capacitance of this capacitor is C. And what we want to do is we want to figure out what is the capacitance in terms of the other variables that are given here. Okay? What is it in terms of maybe Q, A, D, and some other things? All right? Okay. So to do this, let's start off with what was already mentioned. The size of the electric field between these plates. The idea is that if these plates are kind of quite large relative to the distance between the plates here, then the electric field between the plates should be given by the charge density on the plates divided by epsilon naught. Right? Sigma was charge density. This is a result we derived in the past. It can be easily done by using either Coulomb's law, not Coulomb's law, by using Gauss's law. So that's the electric field between the plates. We also know that the size of the potential difference between the plates is related to the electric field and the distance between the plates. It's given by negative E times D. Now, this negative sign isn't going to be more important to us here, so we're just going to be looking at kind of the absolute value of this. So it's going to be just positive ED in that case. Electric field times the distance between the plates. If you don't remember this one, I'll just briefly say that our definition of potential difference was integral of E dot ds, like this. And if the electric field is uniform and the distance d that we traverse goes from, for example, from left to right here, if you go in this direction with your ds, then this just reduces down to, you pull the electric field out, the integral of ds just becomes d. That's how you end up getting negative E times D, if you don't remember that. And I've mentioned before, this is something you really want to memorize because it's going to save you a lot of time in being able to connect potential difference to electric field that you'll have to do from time to time in problems. All right, so that's the electric field. That's the potential difference. We also know the definition of what sigma is. Sigma is charge density, right? So in terms of the symbols that I have written here, what would sigma be equal to?
Q divided by A.
Okay, Q over A. And then the final thing, the piece that we need right here, is that the capacitance of the capacitor, the definition was that you take the charge, divide by delta V, right? So now we're just going to put all this stuff together. And our goal is to come up with an expression for capacitance, right?
Mm-hmm.
You can probably do this yourself if you want to. So what for Q? We replace Q with sigma times A, right? Delta V we replace with E times D. All right. And now we can actually replace E with this, sigma over epsilon naught. So we have sigma A divided by, replace the E with sigma over epsilon naught times D. The sigmas cancel, which is really nice. And we end up getting as a final result that the capacitance of this capacitor is equal to epsilon naught times the area of the plates divided by the distance between the plates. Nice, simple result. You can see that this ends up only depending on the geometry of the plates themselves. Okay, epsilon naught is a constant. It's the permittivity of free space. Area of the plates, distance between the plates. So it's just the geometry of the plates themselves that determine how much charge it can hold. Capacitance is how much charge can you hold per unit voltage, and it turns out it's dependent on these quantities. Let's see if it makes any sense, the answer that we get here. Does it seem reasonable that the amount of charge you can store, that's what this is proportional to the area of the plates? Is that reasonable?
Yeah, that's reasonable.
Yeah.
Because the bigger the plates are, the more room the charges can spread out and stuff like that, right? All right. It's also inversely proportional to the distance. Now, does that make sense? This says that the smaller that the distance between the plates becomes, the bigger the capacitance gets. Does that make any sense?
A little more thinking, but yeah.
Can you provide some kind of argument as to why that would be the case?
So we have a fixed potential difference between these plates.
Right.
So if we're going to bring these plates closer together, then I suspect that more charge would be piling up on those plates. 'Cause, I mean, the potential difference is not changing.
Right. The potential difference in this case is fixed. It's just the potential difference in the battery. That's right. Now, obviously, we can also increase the amount of charge by increasing that potential difference, but it appears that by making D smaller, you can kind of look at this equation, it's going to make the electric field bigger, right? And if the electric field gets bigger, then the charges have to get bigger too. Now, so yeah, bigger area, smaller distance. So what you want to do, if you want to make a really big capacitor, right? What you'd want is you'd want a huge amount of area, as big as you can possibly get, and you want to put the plates as absolutely as close as you possibly can get. Now, it turns out that you don't just have to have air between these capacitors. You can also put something that's called a dielectric in between them. Now, a dielectric is basically any insulating material. And for a given insulating material, so this I really this word is very antiquated. It could just be insulator. This word could just be insulator, dielectric, okay? But it's really any insulating material that you then place between these plates, okay? And for any insulating material, they're going to have something that's known as the dielectric constant. And the dielectric constant is given by the symbol epsilon. Okay, so it's like epsilon naught, but just with, no subscript, right? Then, if you were, for example, to take two plates, okay, and in between the plates, let's say that you placed, I don't know, paper or something like this. Let's say you place a piece of paper in here. And you've got two plates on either side. Well, paper is going to have its own dielectric constant. I don't know what the number is. But what happens then is that the capacitance just becomes whatever that value of the dielectric constant is multiplied by A over D. And I'll tell you that epsilon is always going to be greater than epsilon naught. And that means that you can make a better capacitor by filling it not with air, but instead with something like paper. Okay? Anyway. Maybe I'm getting this name wrong. Maybe the dielectric constant is the ratio of epsilon over epsilon naught. That might be what it is. Regardless, we got this expression right here. Epsilon is always greater than epsilon naught. So the result is that you can make a better capacitor by placing a better insulator in between those plates right there. Okay. In fact, one of the best ways to do this, see how well I can draw this, is to take like a really, really long sheet of, let's say, foil or something like that, because that's a very easily manipulable. Let's say you have a piece of foil right here. And then you put in a layer of paper, a really thin layer of paper. And then you just have another piece of foil on the other side. Like this. Make a little sandwich of foil and paper. And then what you do is you just roll the whole thing up. And that's how you end up producing these cylindrical capacitors that we saw right here, these really big ones. If you were to bust one of these open, what you would see inside is a whole bunch of layers of metal and paper. Not necessarily, it doesn't have to be paper. Sometimes they use different things. But I think if we click up here, where is it? Inside, you can kind of see it. Right? So it's like you've got some kind of plastic insulation on the outside, and then you've got aluminum, and you've got dielectric and metal plates, and you just have several sheets of them that are all wound together like this. Oh, this is a really good picture of it right here. I like this picture. Well, I don't know if it's going to take me to the picture. Okay, so can we click on this? Yeah, that's kind of the idea. So this one has a tissue soaked in an electrolyte. So what this one uses, I believe, is this one actually uses oxidation. So again, let's go back to our definitions here. Where are we? Where's OneNote? That one. So sometimes what they do is they'll basically put two pieces of metal together with some kind of very, very thin separator, and then when they pass electricity through it, it'll cause oxidation. And that oxidation layer, think about like a layer of rust or something like that, for example, that would appear on this foil, becomes the dielectric. And it is incredibly thin because it's a layer of, think about how thin a layer of rust can be on an object, right? So that's how you get a very small D and can get a lot of capacitance. Okay? You have any questions? All right, so before we go into looking at some of the applications of this, I wanted to show you yeah, I think this is true. So epsilon naught is for a vacuum, basically. And these are for non-vacuum. But I'm pretty sure epsilon is always greater than epsilon naught. So let me show you something here. Okay, so if you don't know about this already, this is a website. I'm sure most of you have probably already seen this before. It's called PHET. I'm going to link it in the chat in case for whatever reason you haven't seen this before, because it is extremely useful. I think especially for this course where you're not going to be able to visually see some of the things that we're going to do in class. And this can be really helpful. So what you can do is you can come here. It has little links down here for physics, chemistry, math, or science, biology. So we're going to click on physics. And you've got all sorts of different simulations that you can use to understand physics. Here's Faraday's law that we'll learn about later. Here's Coulomb's law that we've already learned about. Here's a little thing on friction. And they have all kinds of really handy little things here to help teach you. And if that's all too overwhelming, what you can do on the left-hand side here is you can click off all the stuff that's not related to this class and just look at electricity, actually, technically, this is part of this class too. Electricity, magnetism, and circuits, right? And then we've got all these different things. What we're going to look at first, I think I did these in order of how I want to do them here. I think it's this one that we want to do first, right? Okay. So this is just a little, don't take this as being an absolute representation of anything, but it is a good, handy, educational way to understand what a capacitor is. So what we have here is a battery, and we have a capacitor. What we can do is we can manipulate how far apart they are, and we can manipulate how wide the plates are, and there's a limitation to how much we can do. There's also a voltmeter that we can grab right here, and we can use it to measure voltages and things. So we'll do that. The other thing we can do is we can turn, well, first of all, we'll just do this. So let's say we start off with this setup right here. We've got a variable battery right here, and we can basically crank it up to maximum like this. And you can see that depending on what the size of the charge is, or the voltage of the battery is, as the voltage increases up to maximum, you get more and more charges represented here. And they're represented by just a bunch of little plus signs. Okay. The next thing we can do is we can kind of but show what we said a second ago, which is that as we make these plates bigger, there's more and more charge on here. In fact, at the top, you might see that notice that there's a measurement of the capacitance, in this case, based on these numbers given. So here's the area, there's the separation. We could actually calculate exactly what the capacitance is. In this case, the answer ends up being some kind of picofarads. We're going to do a calculation with that in a second. But yeah, this is the epsilon. You basically just take epsilon naught times A over D. You know what epsilon naught is? You've got the area. You've got D right here. Convert everything to meters, and you'll be able to get this number hopefully. Okay. So yeah. So making them bigger, you get you get more charges. Making them closer together, you get more charges. But you can see it's the size of this capacitor is now much bigger. Okay. In addition, we can also highlight what the electric field lines look like between the plates. They look like that. And as we make the plates smaller, the electric field is going to get either stronger or weaker. As we bring them together, the electric field will definitely get stronger. As you get more and more field lines that are packed into that little region right there. All right, so a couple things we can immediately see about this is that if the voltage is at 1.5, if I were to take my voltmeter, okay, and I come and I place it here, and I place it here, that's going to read out the voltage of the battery, okay? And now if I come over to the capacitor and I put this around it, we can see that the voltage of the capacitor is exactly the same. All right, so the battery enforces the voltage across the capacitor plates. We say the voltage drop across these capacitor plates is 1.5. And you always have to measure, you can't measure voltage with just one thing. You need 2 points to measure voltage. So you can know the potential difference between these 2 points, because electric potential is not an absolute term. We have to know the potential difference between 2 points. We can't define what the potential at this point is without also knowing what the potential at this point is and then finding the difference. Okay? All right. So let's look at how such an object like this is affected by a light bulb. So we're going to introduce a light bulb right here. And what we're going to do first is I'm just going to show that if I connect the light bulb up with no charges on the plates, nothing happens. Okay? And now we're going to show how the capacitor can be used to deliver short bursts of energy. So I power up the battery. I charge up my plates right here. Now, one thing that that we can see from this, we can also click on here and see how much energy is stored if we want to. And let's just store a bunch of energy. Let's just make it really just a huge amount of energy. All right, so one thing I want to notice here is, or want to kind of visualize here, is that if I disconnect this from the battery, what do you think is going to happen to these charges if I open this switch right here, like this?
They're just going to stay there.
They're just going to stay there. Let's see. You're right. Now, in reality, eventually they would leak away, but in this type of perfect, ideal simulation, and that's all this is a simulation. This isn't a real battery, obviously. These charges have nowhere to go now. So they're basically just stuck on these plates. You just have this conductor. It's got a lot of charges on it. They have nowhere to go. Okay? They can't jump from this one to this one. Now they could. They could technically jump between the two plates. If the size of the electric field between the plates gets big enough, there'll be an electrical discharge through the air, which would be seen as a shock, like a spark. A spark could technically jump through the air and discharge these plates, okay? I wonder if this is an ideal voltmeter or not. Let's find out. Technically, the charges should be able to flow through the voltmeter too, but I'm willing to bet that this is an ideal voltmeter and they won't, okay? An ideal voltmeter has an infinite amount of resistance to electrical flow, which this one does because the charges are not going anywhere. You connect a real voltmeter up to this, what you would see on this is that the voltage would slowly tick down. Very slowly, but it would tick down. We'll talk about that later on. All right, so now what happens, we can connect. We've got this basically, think about it, this is it's a source of energy effectively now, right? We charge it up with a battery. It's holding all of these charges, and we can discharge it. So what I'm going to do is I'm just going to connect this down to here and just watch what happens with the light bulb. So here we go. It starts off really bright, and it starts to dim over time. And notice as it's dimming, the charges on the plates are going away. What's happening, as you can see here, there's a flow of electrons in this direction. Those electrons are flowing through the light bulb. The light bulb acts as a resistor and kind of turns the flow of electricity into thermal energy, which is then turned into light energy as it heats up the filament. But that's a little short burst of energy. Just to do it again so you can see, so it charges up really fast, right? But then as it tries to dissipate its energy through the light bulb, it starts off with a lot of energy. The rate at which the electrons are flowing is related to the brightness of the bulb. And you can see as the energy is ticking down, the bulb is getting dimmer. So that's the kind of burst of energy you can get. You can think about that as being like, this is like a flash photography thing, right? You, boom, get a big flash, right? So that's why I was saying that these kind of things can be used to store up energy so that you can then flick a switch, boom, and get a huge burst of energy like that. Okay. Does that make sense? Do we have any questions? You can actually, I didn't notice this before, you can actually watch as, let me separate these guys just by a little bit. You can watch as the electric field lines decay here. And as they decay, they basically they spread out from each other, right? Because the density of the field lines is related to how strong they are. And the farther apart the field lines are, the weaker the field. That's kind of cool to see, like as those lines just spreading. It is for me, at least. I don't know if maybe it's boring.
Professor?
Yeah.
Why is it when you switch it and it turns on the light bulb, the capacitance doesn't go down?
That's a great question. So the capacitance, remember, is a function really only of these two variables here. The plate separation and the area of the plate. Let's go back to what we just said. Here we go. That's what the capacitance is. It's epsilon A over D. So if the area of the plates and the distance between the plates don't change, that won't change. But if we change them, see, it changes.
Oh, okay.
It's a really good question.
Thank you.
No problem. Now we're going to add in a dielectric to this. So let's do that. I think that's going to be this one. Yep. Can I make this any bigger? Nope. Guess not. Can I zoom in? Nope. All right. So here's another one. And what this has is it basically just has this little dielectric that I can use. And I can change what it is. Now, the numbers that they're showing here, I'm pretty sure these numbers are a ratio. This is what I was saying earlier. I think the numbers that they're showing here. This might not be what we call the dielectric constant. It may actually be this. A ratio of the two. Because the ratio of these things is always going to be something greater than 1. That's something we're going to talk about more next time. But anyway, so we've got these different dielectric constants right here, or different dielectrics. So let's use glass. So this is a piece of glass right here now. It has the same kind of setup as before, where we can, if we want to view electric field lines, we can look at the size of the capacitance. We can see how the capacitance changes as we, it looks like, zoom out a little bit there. We can see how the capacitance changes as we separate the plates, make the plates bigger, all that kind of stuff. Oh, that's kind of interesting, so we'll do that in a second. All right. So now, we can watch what happens to, let's say, stored charge. Let's use charge. Okay. So right now, there are 0.52 picocoulombs. That's what that says right there. I don't know how hard that is to read, but that's what it says. Oh, you know what I never did? I never made this full screen. I don't know did that have any effect on what you can see on the screen?
It did zoom it in a little bit more.
It did zoom it in, yeah, okay, that's what I thought. All right. Okay, so we've got this capacitor. No, I'm sorry, we have this dielectric right here. I believe these charges are a negative charge overlaid on top of a positive charge, which means this thing is starting off as neutral, in case that was unclear. So what we'll do is we'll basically just slide this in here, and notice something that happens right on the edge right here. As you slide it in, you see how there's a lot more charges that are stored in the region that's where the dielectric is, right here. And as we go inside of here, you can see the capacitance is going up, the amount of charge, we have to zoom out again. The capacitance and the amount of charge go up as we slide this inside of here. How much do they go up by? Well, let's see if this is in any way accurate, because it says that the material glass is 4.7. And what I was saying before is that I think this should increase the capacitance and the charge by a factor of about 5. 4.7 is close to 5, right? Let's see if that's true. So it's 0.16. What's 0.16 divided by 5? It's about 0.03, right? Let's see what happens. Yeah, 0.03. So this literally just kind of magnifies the amount of charge you can store by just sliding this little piece inside of here. And if we were to switch it over to something like Teflon, Teflon has a lower dielectric constant, so you can store less. You'll notice something else that happens here. Let me separate these out so it can be really heavily shown. Within the dielectric itself, the dielectric becomes polarized, okay? It doesn't show it with air, but air would show it too. Or maybe that's supposed to be a vacuum, I don't know. Notice that within the dielectric, you have this kind of like negative, positive, negative, positive, negative, positive. you're supposed to imagine that this is actually molecules or regions of molecules of the dielectric itself that are becoming polarized. Okay, they're becoming polarized. And when you draw in the electric field lines basically go straight through them like that. But by placing the dielectric within this medium, by placing this medium of a dielectric in between these plates, the medium itself becomes polarized. Anyway, so does anyone have any questions? One thing I guess that's interesting to look at with this is to show that if I connect a voltmeter up here, it reads 1.5 volts just like the battery. That is completely unchanged by bringing this in here. That doesn't change at all. Okay. There's a couple other things we're going to use that to show you, but I think this is a pretty good place to take a break. Oh wait, we have time to do one problem. Let's do one problem, then we'll take a break. This problem's really short. Okay, just a simple parallel plate capacitor calculation. So we have the plates of a parallel plate capacitor in vacuum are 5 millimeters apart and 2 meters squared in area. A 10 kilovolt potential difference is applied across the capacitor. We want to compute the capacitance, the charge on each plate, magnitude of the field between the plates. So we've got two parallel plates, one here and one here. The distance between the two of them is given by 5 millimeters. They are 2 meters squared in area, so the area of the plates we could just label as A and say that the area is equal to 2 meters squared. That's huge, right? A meter by a meter. But this is just kind of a educational example. Delta V between the plates is 10 kilovolts, so 10,000 volts. And we want to find the capacitance. Okay, we're going to be using that equation. So capacitance is given by epsilon naught times A over D. You plug in the numbers. Epsilon naught is this number. Let's see, what the units for this are, what is it, coulombs squared over Newton meters squared? Yeah. Okay, that's epsilon naught. We multiply that by the area of the plates, which is 2. We divide by the distance between the plates. You can see that the size of the capacitance is heavily reduced by this quantity right here, by the epsilon naught. Epsilon naught can be thought of as kind of the resistance of space to allow electric field lines to be set up. So, since we're trying to develop an electric field between these plates, that's why it reduces the size of the capacitance and such. So the capacitance of this would be... Go ahead, do you have a question?
Oh no, I was going to say it was 4 times 10 to the negative 9th, or... Oh yeah, that's fine.
This should come out as farads. You can work out these units right here. I might do it during the break. Well, let's see, we can do this easily. Meter squared cancels out with meter squared. You get coulomb squared divided by Newton's meters, which is coulomb squared divided by joules, that's what a farad is. Okay, so that works out. That's the capacitance. This would also be written, since it's 10 to the negative 9, that could also be written as 3.54 nanofarads. That's what C is equal to. Okay, again, just 1 farad is basically equal to a coulomb squared over a joule. So if you want to kind of like work out, not cubed, that's a 2. Yeah, it just looked even worse. Coulomb squared over a joule, which is the same thing as a coulomb per a volt, because a volt is a joule over a coulomb. Okay, that's the capacitance. That's part A. Now let's do part B. Part B says to find the charge on each plate. This is super simple. The charge on each plate, which would be, this would be like maybe plus Q over here and negative Q over here. The charge is given by capacitance multiplied by delta V. Capacitance is 3.54 times 10 to the negative 9 just farads. And you multiply by volts, which is 10,000 volts. And this is like 1E4, right? So this should be 3.54 times 10 to the negative 5 coulombs, which would be, I think, 35.4 microcoulomb. That's our charge. These kind of problems are really easy. In fact, I think you will find that this chapter will be quite a bit of relief by comparison with previous chapters that we've done in this course. This capacitor stuff should be, I hope, pretty easy for you, because it really all comes down to one equation: Q equal to C times delta V. As long as you remember this, you'll be fine. Part C, the magnitude of the electric field between the plates. Oh, look, all the answers are here too. I forgot about that. That must supposed to be an N, I think. Right there. Should be nanofarads. I think I remember making that typo. The magnitude of the electric field between the plates. All right, electric field is equal to, this is where you got to remember that equation, delta V equals E times D. The electric field between the plates should be delta V over D. So it's going to be equal to 10,000 volts divided by 5 times 10 to the negative 3 meters. That was the distance between the plates, 5 millimeters. So that's going to be, what, 10 over 5 is 2. 2,000 times, it's like 2 times 10 to the 6th, maybe? Yeah. Newtons per coulomb. Pretty easy, right? Okay, we'll take a break. In 10 minutes, we'll come back and we'll start doing problems where we combine capacitors in series and parallel, and look at combinations of how those work, and you'll see kind of what's going to show up on your homework in this chapter. And hopefully you find it to be pretty understandable. So we're going to take a break until 10 p.m. No, I swear to God, it won't be hard. I promise you, this chapter is really easy. It's really easy. By comparison, I mean, it's still physics, right? It's still physics, so it's gonna be hard, but it's not. It's a lot easier than the electric field chapter, the Gauss's law chapter, the electric potential chapter. Okay, and the next chapter will be the same way, because we're just gonna talk about current and resistance, and then we'll talk about resistors, and this next month should be, yeah, the first chapter is really hard. I totally agree. All right, so let's take a break.